Hi, statistics. We're going to do a couple more examples in 9.3. And just like we've done before in these videos, I kind of have it written ahead of time for some of them. And so you might need to pause to write some notes in, but I think you will be doing pretty well for this first example. Every road has one at some point, construction zones. And of course, in Wisconsin, we see those everywhere. And in those construction zones, they have lower speed limits. To see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed in miles per hour of a random sample of 10 drivers. Of 10 drivers in a 25 mile per hour construction zone. Here are our results. First one says, can we conclude that the average speed of the drivers in this construction zone is greater than the posted 25 mile per hour speed limit? And then they ask us, given our conclusion in A, what kind of mistake might we have made? A type 1 or a type 2 error? Of course, in order to answer A, can we conclude that the average speed is something other than what is posted? We need to do a significance test. So let's look at what we need. Of course, in our state, we are going to tell the reader what we are trying to find. We will test the following hypotheses at a 5% significance level. They did not tell us what significance level, so 5 is a great one to choose. We need our null and our alternate hypothesis. Our null is that drivers are driving the speed limit at 25 miles per hour, and our alternate is that they are speeding. Mu is greater than 25, where mu is the true mean speed of drivers in the construction zone. Notice we are defining our variables. In our plan, we need to say what we are going to use and check our conditions. So we will use our one sample t-test, assuming random, normal, and independent. Random is, of course, the easiest to check. There is a random sample. Independent, our 10% condition. If our sample size was 10, our population has to be at least 100, and our sample size was drivers on the road. Yes, there are more than 100 drivers on the road. For the normal condition, we have a very small sample, n equals 10, which means we do need to plot our data to see what is happening. As I've mentioned before, to plot your data, you need to, or let me rephrase that, in order to actually get full credit for this, you need to draw out your distribution. Of course, I can drag mine from my calculator. You simply need to sketch a little histogram here of your distribution. But as we look at it, we see that it's relatively symmetric and has no clear outliers, so we are good to go ahead with that normal condition. In our do, we are going to calculate our test statistic and a p-value from that test statistic. In this case, we were not given the mean and standard deviation, we were simply given the sample, which means, yes, you do have to go back to our one variable statistics. Remember, that's under statistics, calculate one variable statistics for list 1, and we get our sample mean is 28.8, and our sample standard deviation is 3.94. Once I have those numbers, I'm able to calculate my t-test statistic of 3.05, and I want to calculate the probability that that or more extreme occurs, the probability that t is greater than or equal to 3.05. One way I can do this is by using tcdf, and I get 0.0069 as my p-value. Notice the things I have that are really important are the formula for my test statistic, the expression for my p-value, my degree of freedom, and then the actual p-value, of course, and the test statistic. Now that I've got my p-value, I can make a conclusion, which is that we are going to reject our null. Our p-value is less than our significance level. 0.6% is less than 5%, which means, again, we reject our null and we have convincing evidence of the alternate. We have convincing evidence to support that the average speed of drivers is greater than the 25 miles per hour that is posted in this construction zone. Now that we have our conclusion, we can think about what kind of error we might have made. Because we rejected the null, we could have made a type 1 error. We make a type 1 error when we reject the null. We say it's not true, but it actually is true. So what would this mistake possibly look like? Well, we're saying we think that people are speeding. We reject the null. They are not driving 25 miles per hour, or we don't think they are. but they really are driving 25 miles per hour. In our next example, we get to talk about a game that, I don't know, I used to play as a kid and really liked. If you've never played it, that's a shame. It's called Don't Break the Ice. The game is played by placing these tiny little plastic ice cubes into a other plastic box, and you will take turns with your partner hitting one of the ice cubes out until the little man on top falls, because you have effectively broken the ice and you would lose the game at that point. Of course, for this game to work properly, the cubes must be big enough so that they hold each other in place, but not too big that they are too difficult to tap out. The machine that produces the plastic ice cubes is designed to make cubes that are 29.5 millimeters wide, but the actual width will vary a little bit, of course. To make sure the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The Fathom output below summarizes the data from a sample taken during 1 hour. Notice, we've seen Fathom outputs like this before, but it's really important to look again, that they have all of these numbers and then a key below. So if we look at this, the count is the second object, 50, which we were already told. We are told that our sample size is 50 cubes, but that might be a good one to check. Then I can see that the mean of my sample is 29.48, so that means X bar is 29.4874. Our standard deviation and our standard error are here. Our minimum, Q1, median, Q3, and max are also here. This problem asks us to interpret the standard deviation and the standard error provided in the computer output, and then do the data give convincing evidence that the mean width is not 29.5. Of course, we need to start with A. So A asks us to interpret the standard deviation, so S of X, and the standard error, SE sub X bar. The first important thing is to make sure we can identify these things. S of X, of course, is the sample standard deviation. And in this case, our sample standard deviation is 0.0935. It's standard deviation. It is the third object in our list. This will be the first one we interpret because it's kind of the easier one. Standard deviation, as we know, is the average distance from the mean. And if we're talking about the sample standard deviation, we could say something like follows. In this sample, our ice cube widths vary from the mean of the sample by about 0.0935, I think it's millimeters on average. Again, average distance from the mean, and if we're talking about the sample standard deviation, it's the average distance in that sample. Now let's look at the standard error. Standard error, first off, if we look in our table, is the fourth item down. So our standard error is 0.0132, I will say. And what do we know about standard error? Standard error, we've seen, is an estimate of our standard deviation of our sampling distribution of sample means, which we know to be sigma over the square root of n. So it's an estimate of this. And if we're talking about the standard error, it's specifically estimating this standard deviation in this sample. So to interpret, we would say something like this. In samples of size 50. In samples of size 50. So notice, I do want to point out, our sample standard deviation is talking about in this sample specifically. The standard error is comparing one sample to another sample because it's looking at the sampling distribution. So in samples of size 50, our sample mean with our X bar will vary from the population mean, which is mu, by about 0.0132 millimeters on average. Again, a very similar thing to what we were just talking about. It's saying samples, excuse me, let me rephrase that. It's saying how something varies from something else. That's what a standard deviation is. Difference from something. But it's just a question of what, difference of what in this. So in the sample standard deviation, we're comparing all the individual cubes in the sample to each other. In the standard error, you're thinking of it like the standard deviation of our sampling distribution of sample means. That standard deviation of the sampling distribution of our sample means is telling me how far any sample mean is from the true mean. And of course, if we're looking at the standard error, we're being a little bit less specific, and we're essentially making an estimate of that. B asks us, do these data give convincing evidence that the mean width is not 29.5? I'm not going to do this problem, I'm not going to do it in class or in this note sheet, but we can talk about two things. The first would be our null and our alternate hypothesis here. Of course, the null is that the true mean is 29.5, and our alternate would be not 29.5, so mu is not equal to, which was what we did the other day in a two-sided test. Whatever we calculate for our t-test statistic, whatever it is, whether it's a positive or a negative, when we calculate our p-value, we are going to be looking at the area in both directions. Our p-value will be the probability that it is greater than the positive or less than that negative. If you would like to do this problem, feel free. I am not going to do it with the class, and I actually don't even have the answer in front of me, but I would be happy to check your work if you do it and see where we go from there. We will come back on Monday I think it's Monday the 13th, right? And we will talk about this example on paired data as an entire class to close out Chapter 9.